Like all the Clickable Calculus webinars, this Multivariate Calculus webinar has two goals. One, clearly want to show some of the Maple tools relevant for multivariate calculus. And two, want to show how a resequencing of skills and concepts as applied to this multivariate calculus course can be implemented in Maple. And now this phrase, resequencing of skills and concepts, comes from the literature. And I ran across it for the first time in the late 1980s when I was getting started bringing Maple into the classroom. What it means is that instead of stressing the development of manipulative skills needed to learn concepts, the process is reversed. The initial stress is on concepts. Development of manipulative skills is postponed until the purpose is seen in light of the conceptual understanding that precedes. Now, this is possible if you have a tool like Maple and you use it for the manipulations needed to examine and absorb the concepts. What I found best was then to implement those skills but use Maple so that you get this big picture approach where the brushstroke details are supplied by Maple. And at this point, mastering the appropriate manipulative skills becomes easier because the implementation, the necessity, and the inner structures have already been seen. The typical Calc 3 course, Multivariate Calculus, starts with a unit on vectors, lines, and planes. I guess this is to get students thinking in 3 dimensions. So let's pick a problem from this section here, lines and planes. I think I'm going to do this problem here, number 10, distance from a point to a plane. So I'll go here to where I can work on the problem, and we're going to find a distance from this point to this plane. I'm going to solve this problem in 3 different ways. I'm going to get a solution using the lines and planes tools that are in the Multivariate Calculus package, and then I'll obtain the traditional solution, but I'll use those same lines and planes tools, and then I'll get the traditional solution without any of the special lines and planes tools that are available. This first solution is just use the powerful tools, lines and planes tools, and get an answer. Okay, so begins by loading the student multivariate calculus package. Here it's tools, load package, and then you go down to student multivariate calculus. That brings into Maple's memory this material. It's there in Maple. It's just library organization, bundle stuff into these neat little clumps called packages. All right, the first stage of direction here says control drag the equation of the plane. So you select the plane, hold down the control key, and move this, pull it to where you want it to go. It's equivalent to copy paste. It's not a Maple thing. It's a Windows thing. I'm in Windows. You can do this in other operating systems. Okay, so the stage directions here tell you use the context panel. So that's here. So in the context panel, you see student multivariate calculus, and it tells you where to go. Student multivariate calculus, lines and planes, you pick plane. That's what this picture here shows you. Maple prints to the screen this thing called a plane object. It's really a module. Think of it as a basket into which all the properties of that plane are tossed. You can rummage around in there and take out what you need as you need it. Then give it a name. So assign to a name. I use Q because it's easy to find on the keyboard. Now, make a sequence of the point 2 minus 3, 1, And a point is represented by a list. That's what the square brackets are for. You make a list, comma, Q. So let's make sure that we can show you that. Go back to Student Multivariate Calculus, lines and planes, and now you see that you're rummaging in the basket with that plane, and you are asking what is the distance between the point that we have next to the name of the plane and the name and the plane. You pick distance, but you get these other things too. You could get projections and intersections and so forth. Okay, so you pick distance, and Maple responds with this exact distance, 29 over the root of 155. And then if you go here to approximate, you can pick a decimal approximation to various number of figures. The second solution, the traditional solution that we'll implement, but we'll use the tools of the lines and planes part of multivariate package. You need a picture. This is a piece of the plane. This is normal to the plane. You need a point on the plane. You need the coordinates of a point on the plane. For the moment, it's the point B. How you find it, we'll worry about that later. That point would be at the base of the normal vector that I've drawn. So there is the point B. By subtraction between P here and B down here, you get this green vector. Project that green vector onto the normal. So here it is in black, projected. That's the component along the normal. I've drawn it here as a separate vector to make it a little bit easier to visualize. It is the length of this black vector. That's the distance that we want. Now we want to implement that solution that we've just sketched out from the picture. Type the name of the plane. It's Q. Context panel, Student Multivariate Calculus, lines and planes. Notice that you have the option of having a point on that plane returned. So Maple returns this point. It really doesn't make a difference which point you use. Here is a point. It comes back as a list. We're going to do vector arithmetic, so we need to convert that to a vector. So conversions here to a column vector, you get the column vector form. And then assign that, give it a name. I've given it the name B. So the green vector is the difference between this position vector to P and the point on the plane B. So here's P. This is B. By subtraction, you get the green vector. So you do the subtraction and give it a name. I've given it the name V. Now we want to get the length of that projection. So here is the vector V. This is the normal. Now where did I get that from? 5 minus 7, 9. Well, just look at the equation of the plane and read it off. 5 minus 7, 9, right? 5 minus 7, 9. You now have the normal to the plane. Okay, make that sequence. Here's the V. Here's the normal. Down here in Student Multivariate Calculus, lines and planes, projection. So Maple will do the projection. That's this vector, and now you want, that's the black vector. Now you want the length of that vector, so we need to find where is the normal. So here's the vector. We want the norm. Click norm, and you get that same number, 29 over the square root of 155. Now, if you didn't have those lines and planes tools, and you wanted to implement that traditional solution, how would you do it? So what Maple would it take to do that? We begin by defining the normal. Now, how I wrote it. N is the name of the normal equals angle brackets to make a vector, and then use assign name, because the name is already there, so I'm assigning the name. I do the same thing, position vector to the point P. Now, to get a point on the plane, pick anything you like for x and y, substitute that into the equation of the plane, calculate the corresponding z value. That will give you a point on the plane. Now, I chose 0, 0 because they're easy numbers to deal with. So here are the stage directions, and here is the implementation of those stage directions. You need the plane, so I did control drag. Now, evaluate at a point, you can set x and y equal to 0, and that will return 9z equals 11. That's what will happen here. 9z equals 11. Then I hit solve, solve. I get the solution, z equals 11 ninths. Now, when you have z equals 11 ninths, you can do a substitute into, and what you want to substitute into is the vector 0, 0, z, and this z will in here will be replaced by 11 ninths, and you will get this vector, position vector, and I'm calling it the point A, so distinguish it from the point B that we used earlier. Then you do the subtraction, P minus A. You get a vector V. I'm using an uppercase V to distinguish it from the lowercase v that I used before. So you now have the green vector, and you want the length of the projection, the green vector, onto the normal. So this is called the scalar projection, okay? V dot n over the length of n. So n over its length, you've made a unit vector out of n. V dot that vector will give you the length of the projection. The dot I get from here. Common symbols. Dot. Now I put that into my favorites palette, and if your favorites palette is not populated, you can get stuff in it by right-clicking, and you add to your favorites palette. That's how I populated my favorites palette with stuff that I use regularly. But you can see we got the same number, 29 over the square root of 155. After the linear stuff in vectors, lines, and planes, start to look at curved things, surfaces. Surfaces are first studied in terms of level curves and plane sections. Let's see what tools Maple provides for that. Here is a surface, and we're going to take a look in terms of a tutor. Where are the tutors? The tutors here are accessible tools, tutors, multivariate calculus. This is the tutor we want to use, cross sections. There are somewhat more than 50. The pop-up tools, and I'm going to access it through the context panel. So let's access that tutor. It requires the student multivariate calculus package. Done some of the typing ahead of time. Control drag down the expression for the surface. Go to student multivariate calculus. You'll see tutors, and you can select cross sections tutor from there. The expression is in place. The default number of cutting planes is 5, and the default range for the z value of those cutting planes is 0 to 32. That's not appropriate here. Look at the scale on the z-axis. This would be better, something like minus 140 to 0. And if we click display, we should get 5 cutting planes. Across that surface, you can see the ellipses that are formed. Turn it and you see a contour plot. Down here you got the command that's doing this stuff. I think it's much easier to use this point and click interface rather than have to learn a whole bunch of syntax in order to make it work, but the command is there. Now you can also get animations. Suppose we picked the 5 cutting planes moving from top to bottom. So you can see the cutting plane moving from top to bottom. You can get plane sections by saying, okay, here's x, and let x run from -3 to 3. Let's take a little bit more than 5. How about we take 10? We don't want to see 10 cutting planes altogether. What we want to do is animate that. Apparently, the animation that was running needs to stop. And there is the animation plane sections. When you close, you get the last graph that you had written to your workspace, and you can use the tools of the toolbar to run the animation. So there's the animation running, and you can do things like run it over and over again, and this one will make it oscillate back and forth, and so now it oscillates back and forth. This is the slowdown. I'm going to let it go at that. So I guess next comes differentiation, and after differentiation, the rudiments of differentiation, partial derivatives. You start doing applications. One of the applications is max-min. So here's a question. Find the extreme points of this function. So it's unconstrained optimization is what it really is. So there are a variety of ways in which these extreme points can be found and analyzed. Graphical, numerical, first approach. All right, so the stage direction says drag down this expression for the surface and give it a name. So I've done that using assign to a name. Then it says type F and press the enter key, so you get this echo back of the rule for the function, and use the plot builder. Now you can access the plot builder from this spot or from here, plot builder, either way. So access the plot builder, which is a pop-up tool for graphing, and you get a default graph, and it's -10 to 5, -5 to 5, and it's hard to see where there might be an extreme point here, so you have to modify the domain and even the range. So the domain works out better if you experiment and you pick. So let's set x between -5 and 2, and let's let y go -3 to 3. And to get the z, you go down here to the view axis. This will go, let's try 8 to 15, and these all came from experiments. And if you basically zoom in appropriately, you can see that this function has a minimum, but is a rather steep, narrow depression here. So you have a minimum here. You want to approximate it numerically, you can use the context panel optimization. Where did that go? Here it is. Optimization, minimize. So local minimization. Here is the value. You can see it's around 9 something. This is the x coordinate, and this is the y coordinate. So you get a numeric graphical estimate of what it is that you're looking for. There's a task template that will do this work analytically. Tools, tasks, browse. That will bring up the table of contents of the task template. So this is the one I want to click on here. Task templates. Okay. Calculus, multivariate, optimization, critical points and second derivative test. So this is the task template. You can install it into your worksheet by clicking one of these two insert buttons. Default content means you get the extra verbiage. Minimal content means get enough to make the thing work. I've got it embedded in my worksheet already. Here is the path to it. Right here, you want to put the letter F, which references the function we're dealing with. The variables are x and y. That's fine. Just hit the enter key. You can see that there are some commands here that are going to get executed. All you have to do is hit the enter key. You need the two partial derivatives. That's what the gradient is doing. It's taking the partial with respect to x and the partial with respect to y. Hit the enter key. And then there is a solve command. So Maple solve command takes each of these expressions, sets them equal to 0, and solves for x and y. The extra coding is to render the solutions as lists of lists. The solve command by itself won't do that. So there's some little extra coding. Hit the enter key. It takes care of it. Turns out there's the one critical point, and this command, second derivative test, explores the list of points and classifies them. There was only one point. It got classified as a local min. There were no points to classify as a local max and no points to classify as a saddle. Now, the second derivative test command can be put to further use. This is the Hessian. It's the matrix of second derivatives. If it's positive definite, that means that surrounding that critical point, you are adding to that value, that minimum value, indicating you have a minimum. If it's negative definite, then you are subtracting, so you have a maximum. You can tell if it's positive definite or negative definite. Because this is symmetric, the eigenvalues will tell you, and here's Maple computing eigenvalues, and here are the eigenvalues. Let's see, square root of 53 is less than the square root of 64. So this is smaller than 8. These are both positive numbers. So you're going to have a local min. Now, if you're going to work from first principles, you're going to have to find the critical points first, and you do that by setting partial derivatives equal to 0. So you can access a partial derivative operator from this calculus palette. It would be this one, partial with respect to x, tab over, put in f. Now you can set this equal to 0 or not. Maple doesn't really care when you hit it with solve and put the template. Now we differentiate with respect to y. Set that equal to 0. Hit the enter key. You have two equations and two unknowns. Solve. Pick the simplest solve. You see you have the minus 17 over 11 and minus 2 over 11. This is what solve returns, but this command up here requires a list of lists, so that's why it had to be coded in such a way to do that. Second derivative test is going to require second derivatives, so we can make use of this calculus palette, a second derivative operator. Oh, I didn't want to put it there, I want to put it here. Second derivative operator with differentiating with respect to x twice. That value is 6. You need the same thing, but with respect to y. Tab F. It's 10. Mixed partial you can get from here. I want to take y second. I want x first. Tab here, put F, control equal. And then you assemble the number fxx, fyy. That's this product. That's 60. Less this mixed partial squared, so it's going to be less 49. And clearly that's a positive number. So that number, test number, is greater than 0, and this number is greater than 0, so your up here critical point is a minimum. Another application of differentiation is the directional derivative. Here's a problem where we look at directional derivative. So we have a point that we want to measure from. We have a direction in which we will make a measurement, and we want to know the rate of change of this function. There's a solution possible from the context panel. Now you can see here it takes the student multivariate calculus package, so let's bring that in. Control drag this expression down. I've done that here. If you then go to the context panel, student multivariate calculus, there will be a directional derivative option under differentiate. Do that here. Student multivariate calculus, under differentiate, you see directional derivative. When you select that, you get this pop-up in which you specify the variables, the evaluation point, and the components of the direction vector. You'll notice that's not normalized. The command underlying this computation does the normalization, and it reports the value of the directional derivative. There's a solution available through a tutor. I've shown you where the tutors can be found. We've loaded the student multivariate calculus package already. We don't have to do that again. So here is the expression, the rule for the function. Multivariate calculus tutors directional derivatives. Up comes this tutor. Here is the rule. It's already in place. The point of at which we want to make our measurement. Let's see, where did that go? That point is 2, 3. You can see it right there, 2, 3. So we make this a 2. We make this a 3. The direction vector, the components are 5 and -7. Display. Well, you get this picture that shows the tangent vector rotating around. But here's the value that this tutor produces for the directional derivative. And finally, a solution from first principles. Keep an eye on that number. See if we can reproduce that number. Now we've got the package installed. We don't have to do it again. You need access to the rule for the function. You need gradient and a unit vector, because if the directional derivative exists, it can be found as the dot product between the gradient vector and a unit vector in the direction that you're making your measurement. Okay, so we want to take the gradient. So optimization, I'm sorry, not optimization, student multivariate calculus, differentiate, and you have this gradient option here. So in this pop-up, those are the variables, and you want to evaluate at 2, 3. 2, 3. I don't know if that takes parentheses or not. Apparently not. So the gradient is this vector, but it is itself enclosed in list brackets, and you want to remove it from that list. So select elements. No, select elements. There's only one in there, so we pull it out. So now we've got our hands on the gradient vector, evaluated at the point 2, 3. We want to give that a name, so assign to a name. How about we call it GF for gradient of F? Okay, so now we can access that gradient vector. Now, we need this vector. Now, you can either use the matrix palette. So here's the matrix palette. You can dynamically choose the size. You put in a template. It's 5 tab -7. That's the vector. You want to normalize that. So student multivariate calculus, normalize. There it is, normalize. You want to give that the name U, assigned to a name U for unit vector. And then you need the dot product between GF dot, and here's my dot operator up in my favorites palette. I think I showed you where that could come from. U, and I believe that will float to the number we saw, 2.5575. Another application of differentiation is constrained optimization, which really means Lagrange multiplier problem. So here is an example. We have an objective function, xy, and a constraint. It's actually a circle. And we're looking for extreme values of this function under that constraint. In order to get started, we need to get some data into Maple. So here I'm bringing in the multivariate calculus package where the Lagrange multiplier command is hiding. And we have these two functions. We write f and we write g. And we use the context panel over here to assign name, makes the assignment. So let's get these two things going. We can get a numeric approximation to the zeros for the extrema that we're looking for with the optimization assistant. So under tools, you see assistants. This particular pop-up tool used to be categorized in here as an assistant. It's still called an assistant, but it's now listed as a tutor. It's right here. This would be the pop-up that we're looking for. I'm going to access it from the context panel. So the stage directions here indicate you make a sequence of the objective function and the equation g equals 0. And in order for Maple to see what that looks like, you hit the enter key. And if you go here to the context panel for that sequence of equations, you see optimization. and it opens up to max, min, and the optimization assistant, and that's what I've indicated here in that little paste in that I've shown. So this brings up the optimization assistant. You have the objective function here, you have the constraint equation here. You can look for a minimum, you can look for a maximum. Suppose you're looking for a maximum, and you say, all right, solve this problem. Well, Maple comes back and says, I can't get started. And the reason why I can't get started is because it's sitting on a point, an initial point, that's too close to an extreme value. So what you need to do is you need to edit and remove the default, let's say 2, 2. And if you now say solve, you get a computation. You have a function value of 1 at the point 1, 1. A nice feature of this assistant is it draws a pretty decent graph. This graph is showing a piece of the objective function's surface, and that curve is the lift of the constraint. And the reason why it's so close to the extreme value is this domain ought to be modified. So I'm going to go minus 2 to 2, minus 2 to 2, and redraw that graph. And you can see the objective function xy is a saddle, and here is the extreme value we found, and this is the lift of the circle up to that surface. And if you select to draw the constraint as a surface, you see the circle lifted, cuts through the surface, makes it a little bit clearer what a constrained optimization problem is all about. And you can now modify, look for minimums, and so forth. You would have to adjust the starting point for the search. So this is a tool that will give you an approximation and some information about the extreme values. And when you hit quit, you get some of that information printed to your worksheet. So now let's look at the Lagrange multiplier method itself. The 3 different ways that we can access it. Context panel is a task template, and then we can do it from first principles. So let's see what the context panel provides. So we begin with the sequence of the objective function and the constraint function, not the equation, just the function. Okay, and we hit the enter key so that Maple can actually see what this is. Go to the context panel. In student multivariate calculus, when Maple sees those 2 expressions, it says, oh, this looks like it's a Lagrange multipliers problem. And you can see I've copied and pasted an image of that. And when you say, let's go, a pop-up dialog comes, and here you put the variables x, y, and you have some choices about what Maple will output. You can just get an answer, value. You can get a more detailed answer, and then Maple draws a picture. And I'll leave you to figure out what that picture is about. I'm going to get detailed, and we'll see how much extra information there is. So what you get are equations giving you the coordinates of an extreme point. You get the corresponding Lagrange multiplier and the value of the objective function. And you get 4 such solutions, 2 up, 2 down. And from the graphical exploration, you should expect 2 up to higher values that were 1 and 1 in 2 different places, and minus 1, minus 1 in 2 different places. So you can access the Lagrange multiplier method from the context panel. Now there's a task template that captures the Lagrange multiplier method. Here's the path to it. we've seen the table of contents for the task templates. Here you would put in the function. Since Maple knows what f and g are, you put in the constraint function, and then you need the coordinates x comma y. And this button actually executes the Lagrange multiplier method. The results are printed in this table, and you read it down. 1, 1 is an extreme point. This is the corresponding Lagrange multiplier. This is the value of the objective function. 1 minus 1, Lagrange multiplier, value of the objective function. So this tutor gives access to the Lagrange multiplier command in a point-and-click fashion. Then finally, an implementation of Lagrange multiplier method from first principles. Now there's several ways you can go about this. You can compute the gradient of f and the gradient of g and make them collinear, or you can write a new function, f minus lambda g, and I've done that here. Wrote f minus lambda g, assigned that the name f, and then the equations, partial of f with respect to x with respect to y, and when you take the partial with respect to lambda, you pull out just the constraint itself, you write those equations, and you solve them. So we could use the calculus palette to get a partial derivative operator. Let's do this one here. It's x, tab over here and put in f. Now you can put the equal 0 or not. Maple solve command doesn't mind. If you don't, it's y, tab, f, tab over, comma, and one more. We need a lambda, tab over and put it in f. These are the equations you have to solve. You set them equal to 0. Now, there's no algorithm for solving nonlinear equations. The only thing that you can tell a student and put into practice yourself is don't cancel anything. You can factor and use the zero principle. Product of two terms equals 0. One or the other or both have to be 0. So here's where having Maple's solve command is a great benefit. If you're going through this with students, they can bog down on solving these nonlinear equations, and they don't understand how to do this properly, or they don't see their way through the mess of solving nonlinear equations. Then they think Lagrange multiplier method is hard, but it's not hard. Conceptually, rather simple. Let Maple do the solving until students become comfortable with this. And finally, if solving nonlinear equations is important to you, then you teach students how to solve sets of nonlinear equations. So let's have Maple solve this. You get back the information, the lambda, the x and y coordinates of an extreme point. You don't get the function value. You can use this information to compute the function value. Another big item in the curriculum is multiple integration. So Maple has a number of tools for that. Here's a problem that will require a double integral. And let's take a look at what Maple has to offer here. So this problem asks for a volume bounded by the planes equals 0, and this surface, this is a plane. So it's a plane above the z equals 0 surface, but the region is inside this right cylinder with cross section in the xy plane, a triangle with vertices 1, 2, 3 here. Okay? Integrating over a triangle generally requires two integrals, because you can only get away with one integral if your triangle is a right triangle with legs parallel to the coordinate axes. So we have two solutions. One is with a task template. Here's the path to that task template. You've seen the table of contents. You can navigate to this task template. I've got it embedded in my workspace. I've also put in the upper bounding surface, and I've put in the vertices of the triangle. So this template will integrate this function over a triangle defined by its vertices. The integration is dy dx. Click here and you see that Maple has figured out the equations of the bounding edges of the triangle and written the appropriate double integral. Here is the integrand. The value of this pair of double integrals is 280. Now, as we go through a solution from first principles, I think what you will realize is this task template gives you an answer with a minimum of fuss and aggravation, because you have to determine the equations of these lines and so forth. Let's see how hard that is with a pencil and paper, and let's see what tools Maple provides for allowing that to take place more easily. So I will make use of the student pre-calculus package because there's a line command in there that will be helpful. So I'm going to re-execute some of this stuff, and I did some typing ahead of time to simplify this presentation so that you don't have to watch me doing too much typing. So F equals, and that's the plane, the bounding plane on top, and I did an assigned name. The vertices are given as lists. I call them P1, P2, P3. I did the same thing. P1 equals, make the list, do context panel, assign name. You can't really do this by hand unless you have a picture of the triangle. So I've drawn this triangle and I've pasted it in here so you can see what it looks like. And I'll show you how you might draw that in Maple. And here are some stage directions that will tell you how to draw such a triangle. This is the first point, P1. This is point P2. This is point P3. And the edges are labeled Y1 to 2. This is Y2 to 3. And this is Y3 back to 1. So here is a list of the 3 points. With the first point repeated so that you close the loop. The context panel provides access to the plot builder here, or you can get it from plots itself down here. Either way, plot builder. Okay, up comes the plot builder. It says options. And you change the style from the default point to line. And you can do a preview and see what you're going to get. And you get this triangle. I think we'll close that. And then you say, okay, draw the plot. You got the plot. Now, I wrote on the plot using Maple's draw on a graph tools. Okay, so you go over here. See where it says drawing, right? You select drawing here and text, and these are little text regions. And that's how I labeled the graph. Okay, so now that you have the graph, you can begin worrying about the equations of those edges. To get the equation of the edges, you've got to do something 3 times. You write a pair of points, P1, P2, P2, P3, P3, P1. These define the segments that form the triangle. Make use of the line command in student precalculus, and the way you get that, let's execute these so I can show you what happens. So two points, student precalculus, lines and segments, line, equation. Gotta hold my hand steady. Line, equation. Okay, and you can see I copied and pasted that little image as a reminder of what you have to do. All right, so the return of that operation is an equation. This is not an assignment. This is an equation. You want this part, the right-hand side, not the y equals. So if you go here to the context panel, you have a right-hand side option, which gives you that right-hand side. And then you want to give it a name. So you assign to a name, use this, and that's where I typed in y12. So if you did assign to a name, you would get a pop-up, and here you would put in y12. Okay, so you have to do that 3 times. P1, P2, P2, P3, P3, P1. That gives you y12 equals, and it is assigned to this expression so that when you type y12, you are getting this expression. Same with y23, y31. To implement the double integral, we'll make use of one of the templates in the calculus palette. So here's the calculus palette. And you can see that I have pre-typed it here. So let's take a quick look at what that pre-calculus double integral template looks like. Now, when you put that template in place, you'll notice the integral signs are dark, they're black. This D is black. That means it's active. If I fill in this template and execute it or hit the enter key, it's going to compute the value of this pair of this double integral. Here, the integral sign is gray and the D is gray, which means it's inert. Now, how did that happen? If you go to the context panel, at the bottom it says 2D math. Convert to. And at the bottom of that pop-up, inert form. That is a conversion from the active form to the inert form. It is the difference between typing int, the command int with a lowercase I, and int uppercase. This is the active form. This is the inert form. So I've filled out the double integral, and it takes 2 of them, because if you look at the triangle, you can integrate from y12 to y31 between 1 and 3. And then from y12 to y23 from 3 to 5. That's the problem when you integrate over a triangle. You have to know where these breakpoints are. So I have filled in. There is the bounding upper plane, F. From 1 to 3, you integrate from y12 to y31, and from 3 to 5 is y12 to y23. Now, without a picture, without some notes to yourself about what you've done, this could be a nightmare. Here you have the equations of the edges. They have names. You put those names in. Maple inserts that. This is the integrand, has the name f. The sum of these two integrals is obtained by this item in the context panel, evaluate integral, and we get the same 280 that we got from the task template.